we start with a little friend called u substitution. So that goes like this. U is equal to x squared plus 1. So du is equal to 2x dx. And so du over 2x is equal to dx. Also, saying that u is equal to x squared plus 1 means x squared is equal to u minus 1. Yeah? Okay, cool. Now, notice that as x goes to infinity, u goes to infinity. Yeah? Okay, so that means that for this lower limit, since u is equal to x squared plus 1, it will be 1 squared plus 1, or 2. This lower limit will change to 2. But for the upper limit, since as x goes to infinity, u goes to infinity, we could just say, for proper grammar's sake, we can just say that this is b, and say the limit is b goes to infinity in front of the integral. Again, the lower limit changes to 2. Yeah, so that means that everything I just said, and then substituting the u's as we need, will start to look like this. Let me not go too fast. Okay, so this 1/2 is from the du over 2x substitution for dx, and so that means that we have the du here and the x there, right? Okay, everything else I've already explained, right? Now, this x is going to turn into x squared because this x here is from this x under du. But there's an x right there. So together they're going to be x squared, right? And remember, we said x squared is u minus 1. So, all right. So that means that we write first x squared times u, because u is x squared plus 1. But then this x squared, as we have already stated here, is u minus 1. So we can write our integrand all in terms of u, and that's like this. Okay, cool. Now, some partial fraction decomposition work. So here goes. Okay, so since this is not a partial fraction decomposition video, I don't think I went too fast, and I just paused enough for you to see the details. Okay, now since far left and far right, we have the same denominators, we only require that the far left numerator be equal to the far right numerator. So that is, we require that 1, which can be written as 0u plus 1 if we so chose, has to equal a times u minus 1 plus bu. This here has to equal that there, right? Because the denominators, again, are the same. Now, here we could distribute the a and collect like terms, so to speak. So that means that we could write this first, and then seeing that au and bu have like a common factor u, we could write a plus b times u. And so we do that, and then of course we have the minus a we had before, right? And that's from a times -1, right? Okay, now comparing this here to this here means that a plus b, the coefficient of u here, has to be the same as the coefficient of u here, which is 0. So that means a is equal to -b, and this constant 1 has to equal -a, which means a is -1. And since a is -b, that means that b is 1. Yeah, okay, here's all that a little bit slowed down and written down. Yeah, okay, cool. And so again, b has to be all right, off grid. Okay, now that's better. B has to be 1. Yeah. Now you can see my secret, how I'm animating it. That's all right. You figured I wasn't performing miracles. Only Jesus performs miracles. All right. So what word 2? Oh yeah, sorry. Now that we've gotten our partial fraction decomposition work done, which is that we know that a is -1 and b is 1, we move forward saying that this here with the known a's and b's is the same as this here, and so that's our integrand. So we see that our integral can be written like this, right? Okay, and that's just again from the partial fraction decomposition work. Now it looks like I'm gonna get rid of this stuff, yes. And so if anyone wants to keep that a secret, see, now you can't see it. Okay. And doing the integration here, this first integral, if we want to see them as two integrals, is like the natural log of u minus 1, right? And then it will be minus a natural log of u. All right, now, so that is like this, right? Okay, natural log of u minus 1 minus a natural log of u. But wait, we remember our log quotient rule. If we have a minus here, we could just do the natural log of this divided by u, right? Okay, so I'm saying using the log quotient rule, we can write that like this. But don't panic, I didn't forget the half. That's right here. So let's throw on the half and let's evaluate from 2 to b. Okay, evaluating from 2 to b means let's plug in b first, and then let's plug in 2, and then put a minus sign in between those two quantities, right? So that means sped up like this, right? And notice I was careful to distribute the 1/2 here, right? Like right there and right there. Now, in this part, let's display what I have to write again. Well, actually, let's backtrack a little bit. So this is what we have to write. You probably trusted I simplified that correctly, and I did. It's like that, right? It becomes this. Okay, cool. Now, as b goes to infinity, look at this argument of log in this part. As b goes to infinity, b minus 1 over b goes to 1. So this whole thing goes to the natural log of 1. Remember, log of 1 is 0, right? And so we see that the first part is 1/2 log of 1, which is 0. And then the second part is minus 1/2 ln of 1/2. This we have to keep. And recalling the what's called power rule for logs, we could put this minus sign right here as an exponent of this argument 1/2. And when we do, what we get is this here, right? But then 1/2 to the negative 1 power is the same as 2. So we could write this, which can finally be written like that. Yeah? Okay, I think my writing gets a little sloppy towards the end. Forgive that. But otherwise, I hope you enjoyed this. Keep watching. Take care.